All right, let's dive into a really clever idea in reinforcement learning today called Expected Sarsa. It's a powerful way to help an AI make much smarter, more stable decisions, essentially by teaching it to think less like a gambler and more like a seasoned weather forecaster.
And really, it all comes down to this question. How do you get an AI agent to see the big picture instead of just, reacting to random one-off events? Well, as we're about to see, the secret is all about teaching it to think about probabilities, just like that forecaster does. Okay, so first things first, let's set the stage a bit. Why do we even need another way for an agent to learn? What problem are we actually trying to solve here? At the end of the day, an agent learns by trying stuff out and seeing what gets it the most reward. It builds up this estimate. You can think of it as a score for how good each action is in any given situation. But as it turns out, there's more than one way to calculate that score. To really get the problem, we've got to look at two of the classic approaches. First, you've got Sarsa, which you can think of as the realist. It's what we call an on-policy algorithm. Now, what that really means is it learns based on the action it actually took, whether that was a good move or a bad one. This keeps it grounded in reality, but man, it can also be super jumpy and overreact to just one unlucky break. Then you have Q-learning, or the optimist. This one's off policy. It always learns from the best possible action it could have taken, even if it didn't do it. It's ambitious, for sure, but it can create this dangerously rosy view of the world, leading the agent to take huge risks based on pure wishful thinking. So this just begs the question, right? Is there a middle ground? Can we create an agent that's more balanced, one that avoids those knee-jerk reactions of Sarsa and the wishful thinking of Q-learning? And that, right there, is exactly where Expected Sarsa comes into the picture. To really get the intuition behind this, we're going to use a super simple, everyday analogy. Let's just forget about agents and algorithms for a second and think about a decision we've all had to make. So picture this. You're heading out the door, you look up, and the sky is cloudy. Simple question. Do you grab the umbrella or do you leave it at home? Let's see how our different agents would tackle this one. The Sarsa agent is a pure realist, so it learns from its most recent, specific experience. It thinks, the last time it was cloudy like this, I got caught in an absolute downpour. And based on that one single data point, its conclusion is simple. Cloudy equals rain, period. The problem, of course, is that that one time might have just been a total fluke. Now, the Q-learning agent, that's our eternal optimist. It looks at the very same cloudy sky and only considers the best possible thing that could happen. Well, what's the best outcome? The clouds part, and it turns into a beautiful sunny day. So it plans for that best-case scenario and confidently leaves the umbrella behind, completely ignoring the much, much higher probability of getting soaked. Okay, so we've seen the realist and the optimist. Now let's see how a smarter approach, the forecaster, handles this. This is the absolute essence of Expected Sarsa, and it's a much more sophisticated way to think. But before we go any further, let's quickly nail down a key term. When we talk about these scores, we're talking about Q-values. Just think of a Q-value as a number. That's all it is, a number that represents how good it is to take a certain action when you're in a certain situation. A high Q-value means, hey, that's a great move. And a low one means, yeah, probably a bad idea. Simple as that. So instead of focusing on just one single outcome, the forecaster's logic is totally different. It starts by listing all the possibilities. It could rain, the sun could pop out, or it could just stay overcast. Then, and this is the magic part, it weighs each one by its actual odds. Let's say there's a 70% chance of rain. By doing this for every single outcome, it calculates a weighted average. This final number isn't based on one random event or some wishful thinking. It's the true expected value of that cloudy sky. So let's just put it all side by side to make it crystal clear. Sarsa bases its decision on one random thing that happened. It's raining, so cloudy is bad. Q-learning focuses on a fantasy best-case scenario. Hey, it could be sunny, so cloudy is great. But Expected Sarsa? It takes the whole picture, the weighted average of everything that could happen. And its conclusion is way more nuanced. Cloudy is probably bad, but, it's not a guaranteed disaster. So now that we've seen the mechanism, let's talk about why this average approach is so powerful when you actually put it to work. There are three huge benefits here. First, it reduces variance. Because it's averaging over all possibilities, it's not going to be thrown off by a single weird or random event. This makes the whole learning process so much smoother. Second, it totally avoids the dangerous optimism of Q-learning by taking all the probabilities into account.
And finally, these two things together mean that expected Sarsa often just learns a good, solid policy more reliably. Now, it does take a little more computation at each step than Sarsa, but that trade-off for stability is often exactly what you need.
This really gets to the core difference in philosophy. Sarsa and Q-learning can feel like a roller coaster, with the agent's decisions swinging wildly based on the last thing that happened or just a hopeful guess. Expected Sarsa, on the other hand, provides a stable, sensible path. It grounds every single one of its decisions in the mathematical average of what's actually likely to happen. So, after all of that, what's the one big idea you should walk away with from this whole explainer? The crucial takeaway is this. To build smarter AI, we need to teach it to make decisions based on the weighted average of all possible futures, not just a single random outcome. It's the difference between just reacting to the world and truly understanding it. So the next time you see an AI making a surprisingly robust decision, you can ask yourself, is it thinking like a forecaster?